Hello, and welcome. Today, we're diving into a story that changed the face of armored warfare forever. An event in the sands of Tunisia, in the bitter winter of 1943, that exposed a shocking truth. A single captured American Sherman tank would shake German confidence to its core and reveal the brutal reality behind wartime engineering. How did a lone tank, still operational after hundreds of kilometers across the North African desert, challenge everything the Germans believed about their tanks? Was it possible that American industrial might, combined with pragmatic engineering, had crafted a weapon more reliable than anything the Germans could produce? Could a tank with a simple, mass-produced transmission outlast, outmaneuver, and outfight the most advanced German designs? Why did the Germans, masters of precision, find their own vehicles repeatedly breaking down in the field while this American tank kept going? And what does this reveal about the true secret of victory in armored warfare, firepower or relentless reliability? All these questions converge on a startling conclusion. The Germans, with their sophisticated but fragile machines, had underestimated the power of industrial maturity and practical engineering. In this video, we will trace the journey of the Sherman from the sands of Tunisia to the testing grounds of Kumdorf, revealing how American factories built tanks that could be repaired quickly, operated reliably, and adapted easily. We will uncover how these principles, shaped by decades of civilian automotive experience, gave the Sherman a decisive edge, even against the most formidable German tanks like the Panther and Tiger. And we will see how this relentless focus on durability, simplicity, and mass production ultimately turned the tide of the war, proving that in armored warfare, the most advanced technology means little if it cannot perform when it counts most. The story begins now, as we unravel how one captured Sherman, dubbed War Daddy II, became the ultimate symbol of industrial strength and engineering pragmatism, an unassuming machine that would forever alter the understanding of what makes a truly effective tank. In mid-February of the year 1943, amidst the vast and arid expanses of Tunisia, a significant event unfolded that was poised to influence the course of armored warfare profoundly. A lone M4A1 Sherman tank, having fallen into enemy hands, came to a halt in the desert's shifting sands. Its distinctive American star was still visible beneath the hastily painted German cross, a stark reminder of the tank's origins. A group of officers from the formidable Heavy Panzer Battalion 101 gathered swiftly around this captured vehicle, notebooks already open in anticipation of examining this unexpected prize. This particular American tank, which had been captured intact and still operational during the fierce battles around Cidboid, would soon serve as a catalyst for a crisis of confidence within the German military engineering community. The implications of this discovery extended far beyond the immediate battlefield. They signaled a fundamental shift in the understanding of armored warfare. The Germans, long relying on superior firepower and armor thickness to dominate their adversaries, were about to realize that a different aspect of tank design, namely automotive reliability and engineering excellence, could be just as decisive. This realization threatened to upend their existing doctrines and reshape their development programs for the rest of the war. The tank bore the name, War Daddy II, painted prominently on its hull, a symbol of its American origins and fighting spirit. With the serial number 123,676,401, this Sherman tank was manufactured by Limer Locomotive Works, a notable producer of military vehicles. It belonged to Company G of the 1st Armored Regiment, part of the 1st Armored Division, a unit well known for its tenacity and adaptability. From the moment of its capture, personnel from a German reconnaissance unit undertook a grueling journey, driving this Sherman over 350 kilometers across the challenging North African terrain to the port of Espifax, a trek that took approximately 4.5 days. Throughout this arduous journey, every kilometer revealed startling truths that challenged deep-seated assumptions about American industrial capability. The engine, remarkably, never overheated despite the harsh desert conditions. The transmission, often a point of failure in many armored vehicles, remained flawlessly operational. The final drives, crucial components responsible for transmitting power from the engine to the tracks, maintained their performance without faltering. German tank crews, accustomed to frequent mechanical stops even during short movements due to the fragility of their own vehicles, watched in growing unease as this American tank proved itself capable of traversing terrain and conditions that would have traditionally crippled or disabled their equipment. Upon arrival at the port, the captured Sherman was carefully loaded onto a cargo ship bound for Germany, a journey that symbolized the significance of this find. The German military authorities had issued explicit orders. This tank must reach the testing facility at Kummersdorf, intact and fully operational, so that they could analyze its capabilities firsthand. While German intelligence had received fragmented reports about American tank production, seeing this vehicle in front of them transformed mere statistics into tangible evidence of a formidable industrial and engineering force. The Sherman, with its mass production capabilities, exemplified a scale of manufacturing that the Germans could not hope to match. Built with principles of automotive engineering that Germany had yet to master fully, this tank represented not just a weapon of war but a testament to American industrial ingenuity. As the vessel steamed northward across the Mediterranean, forward-looking engineers in the Wehrmacht began preparing protocols that would uncover uncomfortable truths about their own technological limitations and about the capabilities of their adversaries. In the spring of 1943, at the renowned Kummersdorf proving ground located just 25 kilometers south of Berlin in Brandenburg, the captured Sherman was unloaded onto a test railcar bearing the designation Zugfahrts 259, with the German license plate WH058941. Test engineers had already meticulously marked every surface of the tank with detailed measurements of armor thickness and angles, preparing for a comprehensive evaluation. Kummersdorf, the primary testing facility for both German and captured Allied equipment, had become the nerve center of armored research and development. Here, engineers conducted rigorous and methodical tests, measuring track tension, assessing transmission efficiency, and documenting every aspect of the tank's performance. Through careful analysis, they aimed to understand not only the American design but also to evaluate whether their own tanks could keep pace with a technological evolution seemingly driven by relentless innovation and industrial might. Their findings in exhaustive technical reports, meticulously detailing every aspect of the examination. The Sherman was on the verge of undergoing what could only be described as the most comprehensive and detailed automotive evaluation ever devised by German engineering standards. This process involved a team of seasoned test engineers, each bringing expertise from various specialized fields within the realm of engineering. These professionals conducted an initial in-depth inspection, photographing every component from dozens of different angles, ensuring no detail was overlooked. They employed precision instruments to measure every gap and clearance, carefully recording the dimensions to ensure exactness. Moreover, they documented the construction techniques used in each part, often finding that the methods employed appeared surprisingly simple, especially when compared to the more intricate, perhaps more refined, German engineering practices. One particular feature that immediately drew the attention of the German powertrain specialists was the tank's transmission system. Unlike German tanks, which relied heavily on straight-cut gears that demanded extremely tight tolerances and required frequent maintenance, the Sherman was equipped with a different type of gear, herringbone-cut gears. These gears are distinctive because they distribute stress across multiple teeth simultaneously, which reduces wear and tear and enhances durability. This gear design had been a standard in American automotive manufacturing since the early 1930s, primarily because it offered a high level of reliability and longevity without the need for the same level of precision that German engineering demanded. German engineers had initially considered the use of herringbone gears to be too complex and costly to produce in large quantities, given their industrial capabilities and the workforce's training at that time. Conversely, American manufacturers had been mass-producing these gears for decades, making their use in military vehicles a practical reality. The testing process commenced with fundamental automotive trials, designed specifically to push each mechanical system to its limits under controlled conditions. The engineers put the Sherman through a series of rigorous tests that simulated battlefield conditions as closely as possible. The tank, nicknamed War Daddy, was driven through obstacle courses that mimicked the challenges experienced in actual combat zones. During these trials, the engineers carefully measured fuel consumption, monitored engine temperatures, and observed the transmission's behavior under varying loads and terrains. After each run, they meticulously disassembled key components to analyze wear patterns and look for signs of stress, inadequate lubrication, or potential weak points in the design. The data collected from these tests painted a picture that contradicted the prevailing German doctrine regarding the fundamental trade-offs between performance and reliability in armored vehicles. The Sherman demonstrated competent performance across all tested categories and, more significantly, showed exceptional endurance, an ability to operate effectively over extended periods without the need for maintenance or repairs, an aspect in which German tanks typically underperformed. This finding highlighted a vital difference in design philosophy. Further inspection of the powertrain revealed fundamental philosophical differences underpinning American and German approaches to tank engineering. The Sherman's transmission system boasted 5 forward speeds plus 1 reverse, with synchronization in gears 2 through 5. This synchronization meant that drivers could shift gears smoothly without needing to double clutch, simplifying operation considerably. As a result, operating the Sherman resembled driving a civilian automobile more closely than the complex, specialized machinery German tanks often required. German tank drivers, by contrast, spent extensive time mastering double-clutching techniques and managing throttle carefully to avoid damaging their more intricate transmissions. The design philosophy of the Sherman assumed that typical soldiers with basic automotive knowledge could operate and handle these tanks efficiently, even under stressful conditions. Meanwhile, German engineering seemed to presuppose that only highly trained specialists would be entrusted with handling their vehicles, given their more delicate and complex transmission systems. The engine powering this particular Sherman, a Continental R975 radial engine, demonstrated impressive resilience and adaptability. Engineers observed that the engine maintained consistent and reliable performance across a broad spectrum of operating conditions and temperature ranges. This was especially notable because, under similar circumstances, German engines often faced overheating or performance drops when subjected to the same demanding conditions. The robustness of the R975 engine contributed significantly to the tank's operational endurance, reinforcing the American design philosophy of durability and ease of maintenance. Powerful yet straightforward in design, the cooling system of the tank proved remarkably effective, despite its simplicity. The air filtration mechanism, in particular, demonstrated exceptional resilience, managing to handle the relentless sandstorms of the North African desert without succumbing to the frequent clogging issues that often plagued contemporary German tanks operating in similar conditions. Every aspect of this vehicle's design reflected a clear philosophy that valued pragmatic functionality over theoretical perfection or overly complex engineering. On June the 6th and 7th of the year 1943, the Hillis-Leen artillery range became the stage for a significant military demonstration. It was here that Reich Minister Albert Schaar arrived to oversee a crucial armament conference, which was attended by key figures from the German armaments industry as well as high-ranking officers from the Wehrmacht. The core of the event involved a series of rigorous tests, including hill-climbing trials that pitted German tanks against captured Allied vehicles to assess their capabilities in real-world conditions. Among the vehicles showcased was the War Daddy II, positioned alongside some of the latest German designs. These included a Panther ACEF Diem tank, freshly produced and ready for combat, as well as a Ferdinand tank destroyer, which represented the most cutting-edge armored fighting vehicle technology in Germany's arsenal at that time. Schaar, who was responsible for overseeing the entire German production of armaments and held a direct line of accountability to Adolf Hitler himself, needed to scrutinize what the American industry was capable of producing and to compare German advancements against the enemy's equipment. The demonstration aimed to reveal truths that neither Schaar nor the German tank designers wanted to confront openly. To everyone's surprise, the Sherman tank, an American design, ascended the test slope with remarkable ease. Its manual transmission, consisting of 5 forward gears synchronized from 2nd through 5th, shifted smoothly without any hesitation, demonstrating refined engineering. The engine maintained a steady power output throughout the climb, further showcasing its robustness. The driver operated the Sherman confidently, exemplifying the effortless maneuverability that would soon become a defining feature of this vehicle. In contrast, the Panther tank, which was powered by a more potent 700 horsepower Maybach HL 230 engine, managed to match the Sherman's performance but only with considerable effort and difficulty. Its greater power did not translate into an overwhelming advantage in this particular test. Meanwhile, the Ferdinand tank destroyer, a heavily armored vehicle weighing in at 65 tons and equipped with an electrically driven transmission system, struggled significantly. As it attempted to ascend the incline, it stalled midway, an embarrassing failure witnessed by all present, including dozens of high-ranking officers and industrial leaders. Recovery crews scrambled to restart the massive vehicle, their efforts visible to everyone, casting a shadow over German engineering prowess during this critical moment. Reflecting on these events years later in his memoirs, Speer recounted his insights into the Sherman's cross-country capabilities, which he had observed during a reconnaissance tour of Italy in October 1944. According to his observations, reports about the Sherman's mobility over difficult terrain had been highly favorable. The tank had successfully climbed mountains that German tank experts believed to be inaccessible to armored vehicles. Speer attributed this exceptional mobility largely to the Sherman's powerful engine, which, relative to its weight, was more than capable of providing superior cross-country performance compared to German tanks. This advantage was corroborated by reports from the 26th Panzer Division, which specifically highlighted the Sherman's ability to navigate rugged terrain with ease. Such findings carried significant weight within Wehrmacht circles, especially given the strategic importance attached to mobility and terrain adaptability. The significance of these observations was publicly acknowledged in an article published in Das Reich newspaper on June 27, 1943. The article praised the Sherman as one of the notable achievements of North American laboratories, describing it as a commendable product of the North American steel industry. It emphasized that the first features to draw attention were, throughout the course of their extensive development, American tank designs exemplified a remarkable combination of rapid construction, rigorous testing, and an almost imperious response to the demanding standards set by the North American automotive industry. These standards, known for their high precision and unwavering quality, resulted in vehicles that not only met but often surpassed expectations in operational performance. Among the innovations highlighted was the gyro-stabilized gun, a groundbreaking feature recognized as the very first of its kind ever produced anywhere in the world. This advancement underscored American ingenuity in military technology, marking a significant milestone in the evolution of armored warfare. Publicly, statements emphasizing such innovations were carefully crafted, serving propaganda purposes by projecting an image of relentless progress and technological prowess. These official declarations intentionally avoided revealing any signs of internal concern or doubts, aiming instead to bolster morale and confidence. Yet, behind this carefully curated narrative, there was a palpable sense of unease within the German engineering community. Private discussions and reports revealed growing apprehensions about the comparative capabilities of their tanks and the limitations of their designs. While American tanks were often described in propaganda as merely adequate, in reality, they were demonstrably superior in terms of engineering quality, especially when it came to sustained field operations. Back in the German town of Kumdorf, a comprehensive testing program persisted through the summer months and into the autumn of 1943, providing critical data on the performance and endurance of the American Sherman tank. Engineers meticulously measured the operational range of the Sherman, conducting extended trials that pushed the vehicle to its very limits. The results were telling. The Sherman's operational range consistently exceeded 2,000 kilometers before requiring significant maintenance, an achievement approximately 4 times greater than what early models of the Panther could sustain under comparable field conditions. They also evaluated the efficiency of the tank's transmission system, discovering that it surpassed German counterparts, with the drivetrain losses notably lower. Such efficiency translated into more effective power delivery and greater overall reliability during prolonged operations. One of the most striking features examined was the Sherman's synchronized manual transmission, which made gear changes smooth and straightforward. Unlike the German transmissions, which demanded double clutching and precise rev matching, the American system required less skill and effort, simplifying field repairs and operation. The final drive system, an essential component determining the vehicle's durability, also presented a noteworthy advantage. German Panther tanks employed final drive configurations inherited from the Tiger design, characterized by straight-cut gears housed within inadequate casings that could not withstand the stresses of combat. These drives were prone to failure under demanding conditions, a problem experienced repeatedly in North Africa and on the Eastern Front, where Panther tanks often had to be abandoned after relatively short movements, sometimes less than 100 kilometers, due to mechanical breakdowns. In contrast, the Sherman's final drives, employing the same herringbone gear principles as the transmission, demonstrated extraordinary resilience. Even under sustained combat conditions, these components rarely failed. Decades later, restoration projects would reveal Sherman final drives that required no mechanical restoration after years of storage, underscoring the substantial safety margins incorporated into their design. Such robustness was a testament to engineering decisions that prioritized durability and reliability over the precise tolerances typical of German manufacturing. By late 1943, The accumulation of extensive data from ongoing tests at Kumdorf allowed the engineers to produce comprehensive internal reports. These documents circulated among the technical branches of the German Wehrmacht and contained critical assessments aimed at senior officers and officials in the weapons ministry. The stark conclusions painted a sobering picture. The Sherman tank exhibited a level of automotive engineering maturity that Germany, despite its wealth of scientific knowledge and technological expertise, had yet to achieve. Although German manufacturing was characterized by high precision tolerances and meticulous craftsmanship, such precision sometimes resulted in vehicles that were less reliable in the field. Conversely, the American mass production techniques, which permitted larger tolerances, produced tanks that, paradoxically, were more dependable during actual combat conditions. The use of interchangeable parts further enhanced logistical efficiency, allowing field repairs to be carried out with basic tools and minimal specialized training. This operational simplicity meant that Sherman tanks could be maintained and repaired quickly by relatively untrained crews, giving them a tangible advantage over German designs that often required skilled mechanics and intricate procedures. The combined effect of these factors underscored the fundamental disparity between the two nations' approaches to armored vehicle design. The Americans emphasized practicality, resilience, and rapid repairability, while Germans focused on precision and optimal performance, yet often at the expense of reliability in the chaos of war. In summary, by the closing months of 2043, the German military's internal assessments recognized a disconcerting reality. The American Sherman tank was not merely a mass-produced vehicle but a product of advanced engineering maturity, capable of sustained and reliable operation under the toughest conditions. This acknowledgement, though often cloaked in cautious language within official reports, marked a turning point in the understanding of technological superiority, highlighting how American industrial strength and pragmatic engineering principles had begun to decisively outpace traditional German approaches, casting a long shadow over the perceived perfection of their armored forces. While German military vehicles were engineered with a level of precision that demanded specialized equipment and meticulous factory work for most repairs, their fundamental design philosophy emphasized functionality and operational durability over sheer performance figures that, while impressive on paper, proved difficult to maintain during combat conditions. The German approach prioritized ensuring that vehicles could sustain prolonged use in the field without constant expert intervention, rather than chasing the highest possible speed or agility that might be unrealistic to uphold under wartime stresses. In contrast, American military vehicle development benefited greatly from a deep-rooted industrial advantage that extended beyond mere production volume. The United States automotive industry boasted decades of civilian manufacturing experience, which was reflected in the widespread ownership of automobiles by ordinary Americans across all social and economic strata long before the war. This extensive civilian automotive tradition meant that American engineers and mechanics had developed practical skills, standardized procedures, and robust supply chains that could be adapted swiftly to military needs. Germany, however, had limited civilian automotive experience. For much of the pre-war period, personal transportation remained a luxury primarily accessible to the wealthy and influential political elites, not the general populace. The ambitious Volkswagen project, which had promised to provide affordable cars for the masses since 1934, was still struggling to produce significant quantities by 1939, with fewer than 1,000 civilian vehicles on the road at that time. This relatively nascent industrial base in automotive manufacturing translated directly into differences in how each country approached armored vehicle design. The disparity in industrial maturity became starkly evident in the way tanks were built and maintained. American tanks were designed with the knowledge that their mechanics, typically trained in civilian automotive repair, could service them effectively using familiar tools and procedures. This approach meant that even in the field, mechanics could troubleshoot and fix issues without requiring highly specialized military technical training. Conversely, German tanks, often assembled in factories by specialists with extensive military education, demanded a level of technical expertise that was difficult to replicate consistently during combat operations. As field reports accumulated through late 1943 and the early months of 1944, the reliability of German tanks, especially the Panther model, drew increasing scrutiny. Panthers were notorious for their fragile mechanical systems, which necessitated strict operational guidelines to prevent breakdowns that could leave them immobilized in combat. Drivers were explicitly instructed to avoid frequent gear changes, as excessive shifting could damage the delicate transmission components. The third gear, in particular, was prone to frequent failure, to the extent that manuals advised its use only when absolutely unavoidable. Furthermore, Panthers lacked the ability to turn sharply while reversing, as such maneuvers would cause catastrophic damage to the transmission. Tactical flexibility was therefore severely limited, since pivot turns could only be performed when the ground resistance on both tracks was equal, a rare circumstance in complex battlefield terrain. The ingress of foreign debris into the running gear further compounded mechanical failures, often jamming the drive sprocket and necessitating hours of maintenance to clear obstructions. All these issues persisted despite the fact that Panthers were produced in dedicated tank factories staffed by skilled workers and constructed from the highest quality materials Germany could procure. Meanwhile, the American approach to tank manufacturing stood in stark contrast. American tanks, particularly the M4 Sherman, were designed by engineers from major automotive corporations such as General Motors, Ford, and Chrysler, which had extensive experience in civilian vehicle production. These engineers applied the principles of mass production, perfected over decades of civilian manufacturing, to the design of military vehicles. The Sherman incorporated commercial automotive components wherever feasible, taking advantage of existing supply chains and manufacturing expertise. Its transmission, for example, was sourced from multiple manufacturers, including Caterpillar Tractor, Buick, and Ford Motor Company. These components were built to identical specifications, with fully interchangeable parts that could be swapped without the need for extensive adjustment or rework. Such standardization, common practice in the American automotive industry, allowed for rapid repairs and simplified logistics, a crucial advantage in wartime. This level of standardization and the use of readily available commercial parts remained largely theoretical in German tank production, where specialized components and unique assembly processes dominated. Therefore, the fundamental difference in industrial experience and manufacturing philosophy directly impacted the operational reliability of tanks from both nations, shaping the course of armored vehicle combat during the war. In the realm of tank manufacturing during the Second World War, a notable challenge arose from the fact that each producer introduced subtle modifications to their vehicles, particularly to the Sherman tank, resulting in a lack of true interchangeability of parts. This variability complicated logistics and maintenance efforts, making repairs more complex and time-consuming. Throughout the years of 1943 and 1944, an increasing number of captured Sherman tanks made their way to Kumdorf, a key location for analysis. These captured vehicles originated from diverse sources, including British units fighting in Italy and Soviet forces on the Eastern Front. Once seized, each of these tanks underwent a systematic series of tests similar to those performed on operational vehicles. This extensive testing created a detailed and growing database of the American tank's capabilities, encompassing various models and production batches. The British, in an effort to improve the Sherman's effectiveness, had modified some of these tanks by fitting them with the powerful 17-pounder anti-tank gun, resulting in the creation of the Firefly variant. This upgrade addressed the Sherman's primary weakness, its firepower, by enabling it to confront German heavy tanks more effectively. German engineers studied these modified Shermans with keen interest. They observed how the large turret ring of the Sherman allowed the installation of the significantly larger 17-pounder gun with only minor modifications, demonstrating a design feature that provided considerable growth potential. This insight revealed that the Sherman's design had inherent flexibility that German engineers had not anticipated when the tank was originally specified. The Firefly's successful adaptation highlighted an important aspect. The original design allowed for future upgrades that could significantly enhance combat performance without requiring a complete overhaul. Meanwhile, the Panther tank, the German response to the threat posed by the Soviet T-34, was rushed into production to counter the Soviets' advanced and highly mobile medium tanks. However, the Panther was not initially designed with the capacity for substantial armament upgrades. Any attempts to improve its firepower would have necessitated a complete redesign of its turret and chassis. To understand the reliability of the Panther, the German military expanded their testing program to include rigorous reliability trials that simulated actual combat conditions. Engineers took the Sherman tanks and drove them through hundreds of kilometers of rough terrain, meticulously recording mechanical issues, maintenance needs, and component failures along the way. These reliability findings were then contrasted with field reports from Panther and Tiger units operating in both the Eastern Front and in Italy. The results painted a stark picture of the Panther's operational reliability. Throughout most of 1943, the average operational readiness of Panthers remained below 40%, with some units reporting catastrophic failure rates as low as 20 to 25%. It was documented that in certain Panther battalions, fewer than 1 in 5 tanks were actually capable of engaging in combat at any given time. In comparison, Sherman tanks demonstrated significantly higher operational availability across all theaters of war. Specific German field reports detailed the extent of Panther reliability issues, providing clear evidence of their shortcomings. For example, during the Battle of Kursk in July of 1943, Panther tanks achieved a mere 16% operational readiness, as mechanical failures rendered more tanks immobile than actual enemy fire. By December of that year, this figure had only modestly improved to 37%. Further reports from February of 1944 indicated a continued level of around 37% readiness, while by April of 1944, it had risen to approximately 50%. A noticeable breakthrough occurred in May of 1944 when operational readiness finally climbed to 78%. These percentages represented the proportion of Panthers available and capable of combat on any given day, with the remaining tanks either awaiting spare parts or undergoing repairs. Although the gradual improvement demonstrated that design flaws and reliability issues were being addressed, even at its peak, the Panther's readiness never approached the consistent operational levels achieved by the Sherman from the outset of their deployment. By December of 1943, the data became undeniable for any objective observer examining the field reports and operational statistics. The engine life expectancy for the Sherman diesel-powered variant exceeded 3,000 kilometers when properly maintained, reflecting its durability and efficiency. In stark contrast, the Panther's engine lifespan rarely reached 1,000 kilometers, highlighting a significant disadvantage in terms of operational endurance. This disparity in mechanical reliability was one of many factors contributing to the overall performance gap between the two tanks, influencing their battlefield effectiveness and logistical support needs. Following a series of engineering improvements, the most critical early issues with the tanks were effectively addressed, paving the way for enhanced operational reliability. By March of 1944, German reports documented that the upgraded engines of the Panther tank could sustain a service life ranging from approximately 700 to 1,000 kilometers. This milestone was seen as a notable achievement, yet it was only a modest step forward in the broader context of tank reliability. To put this into perspective, the improvements brought the Panther's engine durability only to about one-third of what the American Sherman tanks achieved with their diesel engines. The Sherman's transmissions, in particular, demonstrated exceptional robustness. They required minimal maintenance between major overhauls, thanks to the use of synchronized gears that reduced the likelihood of driver error causing damage. In contrast, Panther transmissions demanded near constant attention and frequent repairs, with third gear failures being so frequent that drivers often learned to bypass third gear altogether, shifting directly from second to fourth to avoid the troublesome ratio. Similarly, the reliability of the final drives in Sherman tanks stood in stark contrast to those of the Panther. Under conditions that routinely destroyed Panther final drives within 100 to 200 kilometers of operation, the Sherman's final drives operated with consistent dependability. Field reports from German units that had managed to capture and operate Sherman tanks corroborated the data collected during Kumdorf tests, offering real-world insights into their performance. German mechanized units, finding themselves in desperate need of reliable vehicles as their own tank crews suffered from mechanical failures, eagerly employed any captured American tanks that remained intact and operational. Unlike the Soviet T-34 tanks, which Germans extensively modified before deploying them in combat, the Shermans entered German service largely unchanged. They did not require significant modifications because they functioned correctly right out of the factory, with no inherent design flaws that necessitated correction. Tank crews who had experienced repeated mechanical failures in their own vehicles often expressed admiration for the Sherman's reliability, frequently mentioning it in correspondence and reports as a notable advantage. Reports from panzer regiments highlighted a stark difference in operational experience. Sherman crews could concentrate on tactical considerations and overall combat effectiveness, knowing their tanks were dependable. Meanwhile, Panther and Tiger crews constantly worried about mechanical breakdowns, fearing they might reach the battlefield only to be immobilized by failures or be forced to abort missions because their vehicles could not withstand the rigors of combat without frequent repairs. In January of 1945, during Operation Nordwind, the 10th SS Panzer Division captured 12 M4A3 Shermans at Hellesheim. These tanks, originally belonging to the American 43rd Tank Battalion, had been abandoned by their crews amid the chaos of the German assault but were recovered in an operational state. The 12 Shermans were integrated into the 13th Company of the 10th SS Panzer Regiment and served throughout the remaining months of the war. Their roles included reconnaissance and mobile reserves, roles that demanded consistent movement without the luxury of frequent maintenance stops and relied heavily on mechanical reliability to ensure operational readiness. German commanders recognized a fundamental truth confirmed years earlier through Kumdorf testing. American tanks, especially the Sherman, could be depended upon to perform reliably when called into action. This characteristic of dependability, more than firepower or armor, became a decisive factor in their tactical utility during the final phases of the war. A Sherman tank arriving at a battlefield with a fully operational gun was infinitely more valuable than a Panther boasting superior firepower but broken down 20 kilometers behind the lines. The emphasis on mechanical reliability became even more pronounced during January of 1944, when testing programs expanded significantly as the Wehrmacht retreated across multiple fronts. Additional captured equipment arrived at Kumdorf, including various tank models. Engineers examined the M4A1 Sherman equipped with the Continental R975 radial engine, among other variants, to assess their performance and durability further. This ongoing evaluation underscored the importance of engineering and mechanical robustness as critical components that could influence the outcome of armored engagements, often outweighing the advantages of superior firepower or armor in determining tactical success on the battlefield. During the ongoing battle for technological supremacy, extensive testing and analysis were conducted on various tanks and their different configurations, with particular focus on the Sherman tank and its numerous variants. Engineers meticulously examined the characteristics of these vehicles, benchmarking them against alternative models to understand their strengths and limitations. One notable variant was the M4A2, which was powered by twin General Motors 6046 diesel engines. Tests revealed that this particular model exhibited remarkable fuel efficiency, a critical advantage in wartime conditions where fuel shortages often hampered operational capabilities. Furthermore, the M4A2 displayed distinct operational traits attributable to its diesel power plants, setting it apart from gasoline-powered counterparts. In addition, the M4A3 variant equipped with the Ford GAV8 gasoline engine was also evaluated extensively. This engine was highly regarded by American tank crews, who considered it to be one of the finest power plants installed in the Sherman series. The assessment of these different engines was not merely superficial. Experts scrutinized their performance under various conditions, noting the unique efficiencies and challenges associated with each. Despite the variations in propulsion systems, every Sherman variant shared a core characteristic that stood out to engineers and drivers alike: exceptional automotive reliability. This consistent dependability stemmed from meticulous engineering grounded in robust design principles and the use of high-quality manufacturing processes. Such uniformity was particularly impressive to German engineers, who were accustomed to significant disparities in quality when dealing with vehicles produced by different manufacturers, even if the vehicles bore the same nominal design. The diesel-powered M4A2, in particular, garnered high praise from German military analysts during their examinations at Kumdorf. These tanks, totaling over 4,000 units received via Lend-Lease agreements, played a significant role on the Eastern Front. A notable number of these vehicles eventually fell into German hands during retreats and tactical withdrawals. The twin GM 6046 diesel engines equipped in these tanks provided performance levels comparable to any Sherman variant, but with a crucial benefit: they consumed considerably less fuel than gasoline engines. This fuel efficiency proved to be a decisive advantage as German fuel supplies became increasingly scarce and difficult to replenish. Historically, German designers had experimented with diesel engines for tanks, but the effort was ultimately abandoned due to the significant manufacturing challenges involved and the complex nature of developing reliable fuel injection systems. In stark contrast, American industry managed to produce diesel-powered Shermans alongside their gasoline counterparts without disrupting the overall production schedule. This flexibility underscored the advanced technological capabilities and adaptable manufacturing techniques of the United States during wartime, capabilities that German industry struggled to match under the pressures of constant combat and resource shortages. By March of 1944, reports from General Heinz Guderian, the Inspector General of Panzer Troops, indicated that the reliability of German Panther tanks had improved significantly, reaching what he described as acceptable standards by early that year. Specifically, the lifespan of Panther engines had increased to between 700 and 1,000 kilometers, and the persistent problems with the final drive systems had been largely addressed through targeted design modifications and refined manufacturing techniques. Although these improvements represented progress, they merely brought the Panthers up to the reliability levels that Shermans had maintained since their initial deployment in early 1942. This realization was sobering for the German military, as it highlighted just how far behind their armored vehicle development had fallen. While American tanks had been reliable from the outset, German tanks were only beginning to reach comparable standards after years of incremental improvements. The disparity became even more apparent when considering the broader context. German tank production was hampered by increasing shortages of vital resources and the relentless pressure of Allied strategic bombing campaigns. The Allied air forces intensified their efforts by targeting critical bottlenecks within the German armored vehicle production chain. One major blow came on the night of April 27 to 28, 1944, when the Royal Air Force's Bomber Command launched a devastating raid on the Maybach engine plant located in Friedrichshafen. This operation involved over 322 aircraft and is documented in the archives of the Imperial War Museum as the most damaging air raid on German tank manufacturing facilities during the entire war. The attack not only inflicted severe damage on the engine plant but also destroyed the adjacent ZF gearbox factory, which was essential for the production of tank transmissions. As a result of this assault, the manufacture of tank engines and transmissions at these crucial facilities was halted entirely. The disruption caused by this raid significantly impeded German armored vehicle production, further widening the gap between Allied and Axis capabilities on the battlefield. The strategic importance of such attacks underscored the Allied commitment to crippling German mechanized forces, aiming to weaken their overall armored strength and degrade their ability to sustain prolonged military campaigns. Approximately 6 months passed before production was able to resume in November of the year 1944. However, by that time, the quality control processes that had once been diligent and precise had begun to deteriorate markedly, leading to a significant decline in the overall quality of manufactured vehicles. This decline was primarily the result of the increasing reliance on forced labor, which was being utilized more and more within German tank factories as a consequence of the conscription of German workers into active military service. The shift to slave labor introduced not only inefficiencies but also deliberate acts of sabotage, which further compromised the quality of production. For instance, workers would jam cigarette filters into oil passages to cause blockages, and gaskets were often installed incorrectly, resulting in leaks and mechanical failures. Components were assembled without adhering to proper clearances, which exacerbated reliability issues. Interestingly, these production flaws and sabotage efforts never impacted the manufacturing of the American Sherman tanks, which were produced in factories located safely away from the front lines and combat zones. These facilities were staffed by motivated workers who earned fair wages and worked under decent conditions, ensuring a higher standard of quality and consistency. The fundamental distinction between American and German tank production was not rooted in differences in engineering knowledge or technical expertise. Both sides possessed extensive theoretical understanding and scientific know-how regarding automotive principles. Instead, the disparity lay in industrial capacity and the underlying design philosophies that guided each nation's approach to tank manufacturing. German engineers had a comprehensive grasp of automotive engineering as well as their American counterparts, possessing a wealth of theoretical insight and scientific expertise. Nonetheless, they often failed to apply these principles consistently in their tank designs, opting instead to prioritize other, often superficial, factors. German tanks were designed to showcase impressive performance metrics, powerful guns and formidable armor. Yet this focus often came at the expense of reliability and durability under field conditions. For example, the Panther's impressive 75mm KWK-42 gun and its thick frontal armor came with a significant drawback: an overtaxed powertrain. The vehicle, which weighed around 45 tons, frequently experienced mechanical failures because its engine and transmission systems could not reliably support such a heavy load during prolonged use. Similarly, the Tiger tank, renowned for its formidable combat capabilities, required complex and meticulous maintenance routines, often demanding the expertise of highly trained specialists for repairs. These trade-offs might have been tolerable if German industry could produce sufficient quantities of tanks and spare parts to keep the vehicles operational in the field. However, it was unable to meet this demand, especially as Allied bombing campaigns intensified and shortages of raw materials worsened. In contrast, American engineers, with decades of civilian industrial experience in automotive mass production, designed tanks that could be produced in the tens of thousands. These tanks could also be maintained by mechanics who had received basic training, skills easily acquired from their prior experience in civilian automotive service. The American Sherman's powertrain was assembled from components already proven in commercial vehicles, with design principles directly borrowed from automobile and truck manufacturing. Its electrical system was notably advanced. It included a backup generator capable of powering turret traverse even if the main engine failed, a feature that German designers regarded as a luxury but which proved invaluable during combat. German tank crews could only dream of such conveniences, especially those who had experienced turret traverse failures when their engines stalled on slopes or uneven terrain. These kinds of features were simply not included in German technical specifications, as their designers prioritized armor thickness and gunpowder above all else, often at the expense of crew comfort and operational flexibility. By the spring of 1944, units of the Wehrmacht across all fronts were reporting an increasing number of mechanical problems, a direct result of declining manufacturing quality and the scarcity of spare parts. The Panther, for instance, required transportation by rail if it needed to be moved over distances greater than 100 kilometers, since its final drive components were prone to failure during sustained road marches. In fact, field commands issued explicit orders restricting the movement of Panthers, limiting them to short-range operations or transport to and from maintenance depots, to prevent breakdowns in the field. During the chaos of wartime, ensuring that armored vehicles were ready for actual combat was of critical importance. Failure to do so could mean losing valuable tanks not on the battlefield, but to mechanical breakdowns during their approach marches, when they were most vulnerable. One notable example was the Berger Panther recovery vehicle, which was constructed on the chassis of the Panther tank itself. Its purpose was to recover and repair disabled Panther tanks, yet it suffered from the same reliability issues that plagued the tanks it was designed to service. This recurring problem highlighted a stark reality faced by German armored units. Mechanical failures often led to more tank losses than the enemy's firepower. In some units, reports indicated that as many as 70% of tank losses were due to breakdowns rather than direct combat damage, underscoring how technical fragility could undermine battlefield effectiveness even before enemy action. In stark contrast to German manufacturing, the Allied war effort, particularly in the American sector, continued to ramp up production at an astonishing pace that German industries could simply not match. Over the course of the war, American factories produced an astonishing number of Sherman tanks, more than 49,000, a figure that surpassed the total combined German tank output of all types. These tanks, often supplied in large quantities through the Lend-Lease program, bolstered the armored strength of British Commonwealth forces, who received thousands of Shermans to augment their own units. Meanwhile, the Soviet Union obtained more than 4,000 diesel-powered Sherman variants, which proved vital in their campaigns. Chinese forces operating in Burma utilized Shermans effectively against Japanese armor that was generally inferior in both design and technological sophistication compared to American and German tanks. Every combat theater where Shermans served confirmed the findings from rigorous testing, such as those conducted at Kummersdorf, which had demonstrated the formidable reliability and durability of the American design. When properly maintained, Shermans could operate efficiently under harsh conditions that often incapacitated or destroyed their German counterparts. German tank crews who managed to capture and utilize Shermans consistently lauded their automotive engineering, often commending their ease of maintenance and robust performance in reports, letters, and post-war interviews. On the Eastern Front, German mechanics observed that even the complex Chrysler 57 multi-bank engine, comprising 5 separate engine blocks, was easier to troubleshoot than German tank engines, which required highly specialized knowledge and equipment for repairs. The Ford GAA V8 engine, renowned among Allied crews for its exceptional reliability and impressive power output, also impressed German mechanics, who found it remarkably dependable, a stark contrast to the Maybach engines used in German tanks, which necessitated constant adjustments to valve clearances, ignition timing, and carburetor settings. Furthermore, the General Motors twin diesel engine, which the United States Army had initially rejected in favor of gasoline engines due to perceived reliability concerns, ultimately proved far superior in both performance and dependability compared to any diesel engine German tank industry had developed. Its robustness, combined with the generous design margins incorporated into the Sherman's architecture, contributed significantly to its battlefield resilience. The original specifications for the Sherman's transmission and final drive components were designed for the 30-ton M4 tank equipped with a 400 horsepower engine. These same components proved versatile enough to handle the increased demands of the 52-ton M4A1 jumbo assault tank, which featured significantly thicker armor. Remarkably, the same mechanisms that successfully powered the standard Sherman, originally designed for a much lighter vehicle, also managed to transmit 650 horsepower from experimental engines without requiring major modifications or reinforcement. German engineers, observing these engineering choices, often regarded such overbuilding as unnecessary, considering it mere waste and an increase in production costs that consumed scarce materials without immediate benefit. However, American engineers understood the strategic value of these design margins. They provided ample room for future upgrades, enhanced battlefield reliability, and ensured the vehicle's durability over extended service periods. This extra investment in engineering robustness meant that Shermans could adapt and evolve, maintaining operational effectiveness in the face of ongoing combat challenges. By the summer of 1944, the German military and industrial sectors recognized the significant advantages of the Sherman's design philosophy. While initially dismissive of the American approach, they increasingly appreciated how these over-engineered components contributed to the tank's remarkable reliability, survivability, and capacity for upgrades, which ultimately played a crucial role in the Allied victory across multiple theaters of war. During the intense battles in Normandy, The German tank commanders confronting the relentless Allied invasion quickly realized that their technical shortcomings went far beyond just the capabilities of individual tanks. The disadvantages they faced were amplified by several overwhelming factors, including the overwhelming superiority of American artillery, the devastating effectiveness of close air support provided by Allied aircraft, and the sheer logistical capacity that the Allies could mobilize and sustain. These factors combined to systematically undermine the German forces' ability to hold ground, regardless of the tank models they employed or the tactical ingenuity of their commanders. One of the critical advantages that American forces possessed was the remarkable reliability of their tanks, particularly the M4 Sherman. This reliability was a decisive factor that allowed American armored units to operate continuously for long periods, engaging in offensive actions, maintaining pressure on enemy positions, and executing pursuits without the frequent interruptions caused by mechanical breakdowns. In stark contrast, German panzer divisions were often hamstrung by their limited numbers of operational vehicles, which they had to manage with great caution. Every movement of their tanks was carefully calculated because it consumed precious remaining components and increased the risk of mechanical failure, potentially leaving their units stranded and vulnerable. The disparity in operational readiness and availability of tanks played a pivotal role in determining which side could maintain offensive momentum and which was forced to ration its limited combat resources. From the German perspective, the use of captured American Shermans in combat operations ultimately served as a stark testament to the superiority of American automotive engineering. In December of 1944, during the Battle of the Bulge, the 150th Panzer Brigade, formed specifically for infiltration and sabotage behind enemy lines, sought to acquire captured American vehicles to support their covert operations. Their goal was to leverage the reputation of Shermans for reliability to deceive the Allies and enhance their own chances of success. However, the reality proved disappointing. Despite their strategic interest in the Sherman, the brigade received only 2 of these tanks, and only one was deemed sufficiently operational for movement. Even the operational Sherman never participated in combat, as massive traffic jams and logistical chaos prevented the infiltration mission from reaching its objectives. This failure underscored an important truth. In missions demanding vehicles that could perform flawlessly while operating behind enemy lines and far from any support, American equipment offered the best, if not the only, chance of success. German tanks, regardless of their condition when fully operational, could not consistently guarantee the sustained performance necessary for such demanding operations. By January 23, 1945, the Germans officially acknowledged their automotive failures on a large scale. A significant report from the Panzer Commission detailed catastrophic failures of their tanks' final drives, critical components responsible for transmitting power from the engine to the tracks. The report revealed that across all German tank types, the number of defective final drives was alarmingly high, around 500 in the Panzer IV, 370 in the Panther, and approximately 100 in the Tiger tanks. Additional failures were reported in the Hetze tank destroyer, which was based on a Czech chassis weighing about 38 tons. The findings of this report, presented by General Wolfgang Thoma, who served as the Chief of Staff of the Panzer troops under the command of Guderian, painted a bleak picture of operational capacity. The severity of the situation meant that tanks could no longer be used in an organized or effective manner. Confidence in their vehicles plummeted among the German troops, some of whom abandoned entire tanks altogether, fearing that the final drive failures would leave them stranded and vulnerable to capture. The German tanks, which had been designed to intimidate through their formidable appearance and technical prowess, were increasingly rendered useless by mechanical unreliability, a tragic irony given their initial purpose to inspire fear through impressive technical specifications. The failure to meet fundamental standards in armored vehicle design was starkly evident at the most basic level of performance: mechanical reliability, the essential quality that determines whether a tank can reach the battlefield and successfully complete its assigned mission. By early 1945, as Soviet forces relentlessly pressed toward Berlin, the Kumdorf testing facility was forced to prepare for evacuation. Engineers there hurriedly packed up valuable testing data and shipped documentation to more secure locations further west, aiming to safeguard critical technical intelligence for future analysis, particularly in the aftermath of the war. During this chaotic period, some of the captured tanks, including at least 2 Sherman tanks, were hastily pressed into service with German combat units that were desperately defending the approaches to Berlin. These makeshift deployments turned the captured vehicles into unwitting test subjects, fighting side by side with German-designed tanks in the final, desperate battles. This scenario provided a rare opportunity to observe how these vehicles performed under actual combat conditions, an unplanned, real-world evaluation that could reveal strengths and weaknesses beyond laboratory or controlled testing. The Shermans, once operational, kept fighting until they were either destroyed by enemy fire or abandoned when their fuel supplies were exhausted. Meanwhile, the German tanks, including Panthers and the few remaining Tigers, suffered from high failure rates that astonished even seasoned crews, who were already familiar with the poor reliability of their machinery. Mechanical breakdowns plagued these vehicles at a rate that underscored the deficiencies of their design and manufacturing, contrasting sharply with their seemingly impressive specifications. The story of War Daddy 2, along with dozens of other Shermans tested at Kumdorf, illustrates one of the most profound industrial disparities of the Second World War. While German engineers, working within an industrial system that prioritized theoretical perfection and impressive specifications, produced tanks that appeared formidable on paper, these vehicles frequently faltered when subjected to the rigors of sustained field operations. Their designs prioritized appearance and individual vehicle performance over practical, everyday reliability. In stark contrast, American engineers, leveraging decades of automotive manufacturing expertise and experience, approached military vehicle design with a different philosophy. Their tanks, though often lacking the technological sophistication or cutting-edge features that Germans aimed for, proved remarkably reliable in combat conditions that overwhelmed German machinery. In the harsh realities of armored warfare, the weapon that reliably functions when needed is far more valuable than one that might be theoretically superior but fails when it truly matters. The ability of American tanks to reach the battlefield and perform consistently was a decisive factor that often outshone the more ambitious German designs. Post-war analyses conducted by both American and British intelligence agencies confirmed what the Kumdorf tests had already indicated. A systematic examination of destroyed German tanks revealed that mechanical failures were just as common as, if not more than, damage inflicted by enemy action. Final drives frequently shattered under stress, transmissions seized due to poor lubrication or operator errors, and engines burned out from overheating or insufficient oil supply. Problems that rendered many vehicles inoperable regardless of whether they had sustained combat damage. The German focus on creating vehicles with impressive technical specifications and the pursuit of individual vehicle superiority had blinded them to a crucial aspect of military vehicle design: reliability and ease of maintenance. Many German tanks were so complex that no conscript mechanic could repair them without extensive, specialized training. Their engines, demanding constant expert attention from highly skilled technicians, were supported by a logistics system that, over time, proved to be insufficiently robust, unable to supply the vast and varied parts needed by scattered units operating under battlefield conditions. The lessons learned from the testing at Kumdorf had a lasting influence on post-war German tank development. When West Germany's Bundeswehr began designing the Leopard 1 main battle tank during the 1950s, the emphasis was consciously placed on reliability and maintainability. The engineers involved in the Leopard's development prioritized how well the tank could be kept operational and repaired in the field, recognizing that these qualities were critical for operational success, even more so than the raw technological sophistication or maximum armor and firepower. This shift in design philosophy marked a significant departure from the German pre-war approach and reflected a deeper understanding of what makes a truly effective armored vehicle in modern warfare. The detailed performance specifications of these military vehicles reflect a deliberate and strategic approach rooted in the well-established principles of American automotive engineering. Engineers and designers meticulously studied these principles and intentionally applied them to the development of military hardware, resulting in designs that prioritized durability, reliability, and ease of maintenance. Take, for instance, the iconic Leopard 1 tank. Its design incorporated many of the philosophies that had contributed to the success of the Sherman tank during previous conflicts. This vehicle was equipped with a robust powertrain that provided substantial margins of safety and performance, ensuring it could operate effectively under demanding conditions. Additionally, serviceability was a core design feature. The tank was built for straightforward maintenance that required only minimal specialized tools, allowing crews to perform repairs quickly in the field. Furthermore, the Leopard 1 was built utilizing standardized components, which not only simplified repairs and parts replacement but also enabled rapid field fixes. This modular approach meant that the tank could be quickly repaired or upgraded without the need for a complete redesign, thus extending its operational life and adaptability. As a result, the Leopard 1 evolved into one of the most successful tank designs of the Cold War era. It served with various armies around the world and remained in production for many decades, a testament to its well-founded engineering and strategic foresight. The significance of captured enemy equipment, such as the Shermans taken at Kummersdorf, including one famously known as War Daddy II, still bearing its distinctive name painted prominently on its hull, extended far beyond mere battlefield trophies. These relics represented concrete proof that industrial maturity and sound engineering principles, grounded in practical experience, were far more critical to effective military hardware than theoretical innovations that ignored manufacturing realities. They underscored that engineering success rested on reliable, maintainable designs that could be produced efficiently and operated effectively over the long term. German tank designers, driven by a desire to outpace their adversaries, pursued highly advanced specifications, operating under the belief that superior technology alone could compensate for material disadvantages and numerical inferiority. They assumed that cutting-edge engineering would lead to tanks that could outperform their opponents even in less than ideal production or logistical circumstances. But this assumption proved incorrect. In contrast, American tank builders prioritized reliability, understanding from hard-earned experience that logistics, ease of maintenance, and operational readiness were the true determinants of battlefield success. Their vehicles were designed to be dependable, ensuring that units could stay in action longer and require less support in the field. This pragmatic approach proved to be more effective and ultimately more decisive in the broader context of mechanized warfare. The impact of this reliability-centric philosophy extended beyond individual vehicles. It profoundly influenced tactical armored warfare and reshaped the global understanding of military industrial capacity. While Germany entered World War II with many technological advantages in various weapons systems, possessing advanced scientific knowledge and engineering expertise that exceeded most of their opponents, they lacked the industrial depth necessary to produce these sophisticated weapons on a large scale over prolonged periods. Meanwhile, the United States, despite sometimes having less technically advanced weaponry in specific aspects, possessed a vast industrial capacity to manufacture equipment in overwhelming quantities. This capacity allowed for continuous improvements in quality, reliability, and performance based on real-world combat feedback. The American approach, epitomized by the design and mass production of the Sherman tank, proved far more effective than Germany's focus on technological superiority applied to limited-scale, high-precision manufacturing. Indeed, the United States produced nearly as many Sherman tanks as Germany produced all types of tanks combined. Beyond tanks, American industry mass-produced a wide array of weaponry, supplied allies through the Lend-Lease program, and supported a vast wartime economy that maintained the highest standard of living among all the combatant nations. This extraordinary economic and industrial performance, unmatched by Germany even before the escalation of strategic bombing campaigns, played a decisive role in determining the outcome of the war. It was as influential as any single battlefield engagement, illustrating how the strength of a nation's industrial base can decisively shape the course of modern conflicts. The fundamental truth became unmistakably clear when examining tank performance through an objective lens. Simplicity and practicality often outweighed sophistication and raw specifications. A Sherman tank armed with a 75mm gun that reliably entered the battlefield, fought effectively, and completed its missions without catastrophic breakdowns proved to be vastly more valuable than a Panther equipped with a more advanced gun that frequently failed before engaging the enemy or required 3 days of maintenance for every single day of operation. In essence, the true measure of a tank's worth was not just its firepower or armor, but its operational dependability in the chaos of combat. When assessing the capabilities of a tank battalion, the difference in effectiveness was stark. A unit with around 80% of its tanks operational could carry out complex missions and respond to threats with confidence. Conversely, a battalion operating with only about 40% of its vehicles functioning reliably would face insurmountable difficulties, if not complete incapacity, in executing even basic offensive or defensive actions. This reliability was not merely a matter of convenience or minor technical detail. It formed the core of tactical success. Without dependable machinery, even the most talented crews and well-planned strategies could falter, rendering entire operations impossible. Throughout the duration of the war, German tanks consistently fell short in this essential aspect of reliability. Despite their formidable appearances and impressive specifications, German engineering often failed to deliver consistent performance when it mattered most. American tanks, on the other hand, regularly passed these reliability tests with flying colors. By the middle of 1943, extensive testing conducted at Kumdorf had left no room for doubt. American designs boasted mechanical robustness and operational durability that its German counterparts could not match. German commanders, still entranced by the allure of the Panther and Tiger tanks, powerful-looking machines with outstanding technical features, persisted in deploying these vehicles despite mounting evidence that they could not be depended upon in critical moments. The victory of the Sherman tank in World War II was not primarily due to superior firepower or armor protection. Instead, it stemmed from a different kind of strength, industrial superiority manifesting as mechanical reliability, unwavering availability, and ease of maintenance. American industries, having developed these qualities over decades within the civilian automotive sector, extended those well-honed principles directly into military production. By contrast, German engineers had not cultivated the same level of reliability, nor did they adapt their manufacturing processes to prioritize consistency under wartime conditions. Midway through 1943, German engineers at Kumdorf recognized this fundamental disparity. Their comprehensive, meticulously documented research confirmed that American vehicles, exemplified by the Sherman, benefited from a level of industrial maturity that German industry simply could not match at that stage of the war. Their scientific investigations, which repeatedly tested and verified their findings, conclusively demonstrated that American tanks excelled not because of cutting-edge specifications alone but because they embodied practical, reliable engineering. However, understanding the nature of the problem was only half the battle. Finding effective solutions posed a far greater challenge. German industry lacked the capacity and resources to reorient its entire production system toward prioritizing reliability, especially while embroiled in a war on multiple fronts against enemies equipped with far greater material resources. Meanwhile, American industry drew upon a long history of automotive manufacturing, where reliability, ease of repair, and consistent performance had been refined through fierce commercial competition. These principles were seamlessly transferred from civilian vehicles to military tanks, resulting in equipment that was not only durable but also easy to produce, maintain, and repair under battlefield conditions. The story of War Daddy II, the single Sherman tank captured in Tunisia and rigorously tested at Kumdorf over several months, encapsulates this reality. Every kilometer it traveled without failure was a testament to American industrial expertise. Every data point confirmed that the American approach to tank design had, at its core, a fundamental focus on reliability over mere specifications. Its performance starkly contrasted with the German approach, which often emphasized impressive technical features while neglecting the practicalities of consistent operation. The exhaustively documented tests in Kumdorf provided irrefutable proof that American automotive engineering, built on years of experience and mature manufacturing processes, had a decisive advantage. These tests demonstrated that industrial maturity, combined with practical manufacturing know-how, mattered far more than theoretical performance calculations or spectacular specifications. The reliability tests, which consistently showed Sherman tanks outperformed their German counterparts, underscored a vital truth. The Americans had effectively solved the problems that plagued German tanks. German engineers, despite their technical expertise, had failed to recognize the importance of reliability as a core design principle. They did not realize they needed to develop solutions that emphasized durability and consistent performance, and as a result, their tanks often proved fragile in actual combat. The Sherman, in comparison, was an unremarkable machine in many respects, just one among nearly 50,000 units produced, but it carried within it a profound and devastating message. It symbolized the fact that Germany had, by that point, already lost the industrial war, even as fierce fighting continued on the battlefield. The American industrial capacity had reached a level of maturity that rendered German efforts to he was able to secure a victory regardless of the complexity of German technological advancements or their tactical expertise.